So, our starting point this evening is our Earth is warming, our ice is melting, and our sea level is rising. So we can be confident in all of those statements, and that's because they're all measurable. We can measure the change in temperature, we can measure the change in ice volume, and we can measure how sea level is rising. And what's more, the temperature change that we're seeing is due to human emissions. It is due to, again, we can be confident in that statement, it's due to human activity on our planet. We can also, and we can be sure, we understand those processes. We understand the processes around greenhouse warming. We can measure the change in atmospheric chemistry, the greenhouse gas changes in the atmosphere. From pre-industrial levels to today, they've gone up about 33% to a present-day value of 400 parts per million for carbon dioxide levels in the atmosphere. And some of the subsequent speakers, I'm sure, will talk about that level that we've reached of 400 parts per million carbon dioxide in our atmosphere. The predictions are that sea level will rise approximately a metre. That's the sort of generally accepted figure by the end of the century, by 2100. However, the sleeping giant here really is Antarctica. It's on our doorstep, and that's why it's so important to New Zealand. And that's why we made the effort to bring the SCAR conference to New Zealand. We've been discussing for a day and a half now, two more days to go, the changes that we're currently seeing in Antarctica. But it's not just those changes in Antarctica. It's really those changes, it's how those changes impact the rest of the world, including New Zealand. We're lying in the pathway, that's for sure. So, Antarctica has a huge volume of ice. It's up to 4 kilometers thick in places, sitting on top of the Antarctic continent. If all that was to melt, that would raise sea level by approximately 60 meters. But the real question is, how stable is that ice in Antarctica? And what contribution is Antarctica going to make? And do we understand those processes that are going on and the contribution that Antarctica is going to make? So there are some of the issues we hope we will touch on this evening. So to start the ball rolling, I want to introduce our first speaker, and that's Jonathan Bamber. As you've already heard, he's Professor of Physical Geography and Director of the Bristol Glaciological Centre at the University of Bristol in the UK. He graduated from Bristol University with a degree in physics in 1983, went on to complete a PhD in glaciology and remote sensing at the Scott Polar Research Institute in Cambridge. He then spent 8 years at the Department of Space and Climate Physics at the University College London before returning to Bristol, where he is now. But his interests are in the application of satellite and airborne remote sensing data in the polar regions. So he's going to set the scene tonight. He's going to talk about the changes in the Arctic and the Antarctic. So, Jonathan.
So, thanks very much for the introduction, Brian. As Brian said, my area of specialisation is satellite remote sensing of the polar regions, and most of the work that I've done has been on Greenland and Antarctica. I'm going to give you a whistle-stop tour in the next 15 minutes of some of the basics around how we make the observations and what those observations have told us about the ice sheets. Some of it is quite a basic introduction. I hope it's not too patronising for you. Quite a mixed audience, so there's some introductory material in there. The detail is going to be filled in by some of my colleagues who are going to expand on some of the points that I don't have time for now. So very quickly, what are the factors that influence sea level rise? There are several different components. There's changes in terrestrial water storage and the hydrological cycle. That's a relatively small component. There's changes in land movement, that's tectonics and subsidence. Again, that's a relatively small component. You've got changes in ocean circulation, which is significant on the short term, but doesn't actually change the volume of ice, the volume of water. It moves it around, so you might get increases in one place and decreases in another. The two most important factors, and the two I'm going to concentrate on here, are what's called the thermosteric component. That's as the water warms, it expands, and its density changes due to changes in salinity. So that's called thermosteric. The largest component of that is the thermal component. And the other major component is the contribution of glaciers and ice sheets to sea level. A little bit of background about why we care about sea level. Again, you know, most of you probably know all this, but this is quite an old slide. It's actually from before 2010, but it just illustrates the point that there are a very large number of mega cities. Those are cities with populations exceeding 8 million, lie in coastal areas, actually right by the coast, which are susceptible to relatively small changes in sea level. I don't know why London isn't on there, because London is a mega city with a population of over 12 million. And the Thames Barrier, which is a multi-billion pound flood defence system for the River Thames, is already reaching its end of life about 30 years before it's expected to, because of the acceleration in sea level rise that we've experienced recently. And I mean, Auckland isn't on there because it's not a mega city, but it's a coastal city which is also susceptible to sea level. A couple of slides on what's happened in the past, and this is to set the scene a little bit. This is a reconstruction of sea level since something called last glacial maximum, when we had ice sheets covering North America, Eurasia, and Antarctica was about 10% bigger than it was today, and Greenland was about 10% bigger. And you can see on the y-axis here you've got relative sea level, and on the x-axis time going backwards to about 22,000 years ago, when we had maximum ice cover. And you can see that the sea level record here, or sea level, is negative. So in other words, sea level was about 120 metres lower than present when we had all this ice cover. And when the major ice sheets in the northern hemisphere started to melt, you got this increase in sea level from about 18 years BP up to about 8,000 years ago. And the mean rate of sea level rise over that period was about a centimetre a year, so that's a metre a century. Now that's a pretty serious sea level rise if it happens in the next century. A metre is pretty serious for things like loss of coastal areas and migration. There's an event here called Meltwater Pass 1A that took place about 16,000 years ago, where the rate of sea level rise was 4 times larger. It was 4 metres a century. Now this was at a time when there was an ice sheet covering North America, and probably a significant component of this came from North America. Some of it, we believe, also came from Antarctica. The point for showing you this is that the paleo sea level, paleo climate record, shows us that ice sheets can do pretty dramatic things. They can lose mass very rapidly, and they can result in sea level rises of, in this case, 4 metres a century, sustained over about 400 years. So, I mean, I'm not suggesting that that's going to happen in the next century, but what that does tell us is that ice sheets can do quite dramatic things. This is the sea level record for about the last 100 years, slightly longer. Most of it is from tide gauge data, so these large error bars on the y-axis here indicate quite big uncertainty from a quite sparse record of tide gauge data that goes back to about 1860. What this shows is that hopefully you can see that sea level has been accelerating over that period. If you take the mean for the 20th century, it was about 1.5 millimetres a year, which doesn't sound a lot. It's 15 centimetres a century. What the satellite record, the most recent and most accurate data show us from the last 20 years, is that the rate of sea level rise has almost doubled in that period, and it's around about 3.3 millimetres a year now. That's over 30 centimetres a century, and obviously if it carries on accelerating, it's going to be significantly more than that. If we zoom in to the most recent 20 years. This is from a combination of satellite data and buoys around the ocean that measure sea surface temperature. This is the thermosteric component, and you can see that it's about a third of the sea level contribution, and 2/3 comes from changes in mass of the ocean. And almost all of that, a small amount is due to land water storage, but almost all of that is due to melting of glaciers and ice sheets around the world. So about 2/3 of recent contribution. And so the acceleration in the last 20 years, the increase in sea level rise, has also come from an increase melting of glaciers and ice sheets around the world. Yeah, I think that's all I need to say about that. So, as Brian said, I'm going to talk about all ice on the planet, focusing on Greenland and Antarctica. Those are the biggest ice masses. But it's important to mention what glaciers and ice caps have been doing as well, because in the past, actually, they have been the dominant contribution to sea level rise. In, say, between about 1950 and 1990, they contributed more than the ice sheets. And this is a plot just showing land ice cover and sea ice in the northern and southern hemisphere. The yellow shows glaciers and ice caps. And what's the difference? Well, it's just one of scale. So there are two ice sheets on the, there are three ice sheets on the planet. There's Greenland, there's West Antarctica here, and East Antarctica. My colleagues will explain why the two are just sort of separated in their talks. And you can see that the glaciers and ice caps are, in terms of area, a very small proportion of the total ice cover. By far, the most significant components are Greenland and Antarctica. And Antarctica is actually 10 times bigger in area and roughly 10 times bigger in volume than Greenland. This is those ice masses to scale. So this is Antarctica, Greenland. This slide was produced for a UK audience. That's the European Alps, not the Southern Alps, but you get the idea. It's pretty small. And that's the UK to scale. So Antarctica is a pretty big place. As Brian said, the ice is up to 5 kilometres thick. It's about 1.5 times the area of Australia. It's larger than conterminous USA. Something like 80 to 90% of the global freshwater supply is locked up in the ice sheets of Greenland and Antarctica. If you melted, and I'm not suggesting this is going to happen, but if you melted Greenland tomorrow, the contribution to global sea level will be about 7.3 metres. For West Antarctica, it's about 4 metres. For East Antarctica, it's about 53 metres. And glaciers and ice caps, although they respond quite rapidly to changing climate because they're much smaller, if you melted them all tomorrow, their contribution would be around about 0.5 metre. So their potential to increase sea level in the future is very much smaller than the ice sheets. And you can see here, by far the biggest potential, the giant, the sleeping giant that Brian talked about, is East Antarctica, which is an order of magnitude bigger than the other two. Just a couple of slides on the sort of work that I do and how we actually know what the ice sheets are doing and what the sea level has been doing. Our most reliable estimates of ice sheet change come from satellite observations, because they're so big. You know, it's 5,500 kilometres across Antarctica. The only way we can get synoptic observations is from satellite data. And those reliable observations start in 1992. That's just over 20 years ago. So we have a really very short record of what the ice sheets have been doing, reliable record, and that's quite important to bear in mind. They started with something called radar altimetry, and then more recently laser altimetry. Altimeters measure surface elevations very accurately. A laser altimeter can measure from an altitude of 1,000 kilometers changes in surface elevation of a few millimeters. The technology is really quite staggering. And another type of satellite measurement that is also pretty remarkable is something called GRACE. That's a satellite that measures small changes in the gravity field. In fact, it's 2 satellites separated by about 200 kilometers, and there's a microwave. It's almost the same as an altimeter. It's a microwave ranging device that measures the distance between 2 satellites to an accuracy of a few microns. And that difference in distance between 2 satellites is it reflects changes in the gravity field of the Earth, and so we can measure very small changes in mass distribution on the surface of Earth using this technology. It is absolutely phenomenal. It's, you know, to coin a phrase, it is rocket science. This is what the results from one of those satellite sensors called ISAT. That was the laser altimeter. This is mean elevation changes over about a 7-year period for both Antarctica and Greenland to scale. And there's some very important things to notice here, both in Antarctica and Greenland. So around the margins of Greenland, the red shows thinning, and it's quite dramatic thinning. And this is thinning, in other words, ice loss that's taken place quite recently. Most of the margins of Greenland have thinning. And there's one area of Antarctica, of West Antarctica, this area here, that my colleagues are going to talk more about in their presentations, called the Amundsen Sea embayment, or Amundsen Sea sector of Antarctica, where the thinning is really very marked. And this is a particular concern for glaciologists, because we think this part of Antarctica is potentially unstable, and there may be a rapid reduction in ice, not possibly a collapse of this part of the ice sheet. So that's the kind of technology we use for making these observations. For glaciers and ice caps, remember they're smaller, but there are a lot of them, we have quite a long record of in situ observations. These are people going out into the field actually measuring the mass balance of glaciers. And we've got actually data going back much further than 1960, but global coverage is pretty good for about the last 50 years. And this is the trend in what's called sea level equivalent, so in millimeters of sea level rise from glaciers. There's these different colours represent different estimates from different authors and different techniques, but you know they are showing a general increase, almost a doubling in the contribution of glaciers and ice caps over about the last 50 years, from about 0.5 millimetre a year in 1960s to around about 1 millimetre a year now. But remember that even if we got rid of all of them tomorrow, the total contribution would be about 0.5 metre. This is what the satellite record, and it's only 20 years of data, tells us about the ice sheets. So we've got in red Antarctica, blue is Greenland, and green is the sum of the two. So in the early 1990s, we're pretty confident that both ice sheets were roughly what's called imbalanced. They weren't losing mass, they weren't gaining mass. And over this 20-year period, both ice sheets have started to lose more mass, and that loss has accelerated to the point where now the 5-year mean contribution of Greenland and Antarctica combined is getting up to about 1.2, 1.3 millimetres a year. So it is now the most dominant component of sea level rise. Prior to 1992, well, we know that from the sea level record, we know that sea level rise was about 1.5 millimetres a year, and we have a fairly good handle on the thermospheric component, thermal expansion. But really, we have no robust direct observations of what the ice sheets were actually doing. We can only infer indirectly from the sea level record. Couple of points about what sea level rise looks like around the world. Most people, when they're talking about sea level rise, they just, I've just done it in fact, you talk about number, 5 metres, 1 millimetre a year, whatever it is. But actually there are very substantial regional differences. And those regional differences are due to how much heat is, where the heat is absorbed by the ocean where the heat uptake takes place, and quite a complex process which is due to the changes in the gravity field of the Earth as ice is melted on land and enters the ocean. And those two effects can be seen in the observational record here of sea level rise over the last 10 years. Well, it's over a 10-year period. And what you can see here is that, remember, the mean rate over this period was about 3 millimetres a year, but the scale here is 5 times larger. And there's a maximum in the Western Pacific, actually around New Zealand, and the atolls in the Western Pacific like Maldives and Micronesia. And the rates there are about 1.5 centimetres a year. Now, if they were sustained over a century, that's it's extraordinarily serious for those areas. As I said, one of the surprising effects of ice melt is this regional variation in the contribution due to changes in the gravity field. And what that means is that when you have ice melting around Greenland, sea level actually goes down. It gets lower because the gravity field, the amount of mass over Greenland is going down, and therefore less water is pulled to Greenland comparatively, because the ocean follows what's called it's a geopotential surface. It's the gravity field, and so if the gravity gets weaker around Greenland, sea level goes down, and the same thing happens around West Antarctica. But what you find is that you get a maxima again in the Western Pacific, around New Zealand and these small islands and low-lying areas. There's a second effect which is also, it's called true polar wander, because the mass loss is not actually centered over the axis of rotation of the Earth. The axis of rotation changes very slightly, and that means the water sloshes around in the east-west direction as well. So that was a very brief kind of introduction to what the ice sheets are doing right now in the last, well, what we know about, what we know they've been doing in the last 2 decades, and a few take-home messages here. Both glaciers and ice sheets their contribution has been accelerating in the observational record. The rate of acceleration of ice sheets has been significantly greater than that of glaciers, and any other contribution has been greater than that of thermal expansion as well. And ice sheets, our colleagues will say more about this, they have the largest potential and the largest uncertainty for future sea level rise. And there is one thing that we can be certain of, which is if you warm the planet, ice is going to melt.